Harvard researchers achieve breakthrough in miniature. UV light generation scientists at Harvard University have successfully demonstrated a way to generate powerful ultraviolet UV light directly on a microscopic chip. By utilizing a specialized material and a novel fabrication technique, the team has overcome a long-standing hurdle in photonics: the tendency for UV light to lose strength rapidly when confined to tiny circuits. The challenge of shrinking UV technology ultraviolet light is indispensable to modern high-tech industries. It is a cornerstone of sterilization processes, biological imaging, and advanced semiconductor manufacturing. Looking forward, compact UV sources are essential for the next generation of technologies, including ultra-precise atomic clocks and quantum computers. Historically, integrating UV light into small-scale chips has been difficult. While engineers can easily guide infrared or visible light through microscopic channels, waveguides, UV light is notoriously difficult to manage. It tends to dissipate quickly as it travels, making it nearly impossible to create efficient, high-power UV sources at the chip scale. A new approach: frequency upconversion rather than trying to guide existing UV light through a chip, which leads to massive energy loss. The Harvard-led team, directed by Professor Marco Lanchar, decided to create the UV light internally. The researchers used a material called thin-film lithium niobate. This crystalline material is a staple in telecommunications because of its ability to manipulate light, but it is not typically associated with UV applications. The team employed a process known as frequency upconversion. Red light, lower energy, is sent into the lithium niobate crystal. Inside the crystal, two red photons are combined. This combination results in a single, higher energy UV photon. The innovation: sidewall polling. The breakthrough relies on how the crystal structure is manipulated to facilitate this conversion. To make the process efficient, the crystal's domains must be flipped at precise intervals along the waveguide process called polling. Previously, researchers faced a dilemma. They could either polish the entire film, which left no room for error correction, or build the waveguides first, which resulted in poor efficiency, because the control electrodes were too far from the light path. The Harvard team solved this with a high-precision technique called sidewall polling. They positioned microscopic metal fingers directly along the sides of the waveguide. These electrodes are placed with 50-nanometer accuracy. By applying voltage through these side electrodes, they can flip the crystal domains across the entire cross-section of the waveguide. This precision ensures that the light interacts with an optimally structured material, maximizing the energy converted from red to UV. Results and future implications: the results, published in Nature Communications, represent a massive leap in power output. The device produced 4.2 milliwatts of UV light at a wavelength of 390 nanometers. To put this in perspective, this is roughly 120 times more powerful than previous attempts using thin-film lithium niobate, which only produced tens of microwatts. This increase in power moves the technology from a mere laboratory concept to a practical tool. The implications are significant. Quantum computing. Scalable quantum computers require light sources that can be shrunk down to the chip level. These devices could provide the necessary UV light for trapped-ion quantum systems. Environmental sensing. The same technology could lead to compact, highly sensitive sensors capable of detecting greenhouse gases and air pollutants in real time. If you want a scalable quantum computer that isn't the size of a truck, you need to scale everything down to the chip level, and this includes the light sources. Conclusion: by mastering high-precision, sidewall polling, researchers have unlocked the ability to generate high-power UV light on a microscopic scale. This breakthrough paves the way for miniaturized, highly efficient components in quantum computing and environmental monitoring.